So as Stefan said, I will talk about the new developments in Triscam. So some of them you have already seen a little bit. So new resins that are not so new. Ines talked about the TKI synth for the chlorine and eventually iodide measurement in our presentation just in the session before. And Ibak just talked about the TK202. The TK200 resin is not so new, but it's not so much known, so that's why I present it here. On the new resin, there is the TK221 and the TK. So this one I will talk about it, but on the TK222 is also a new resin, but it's mainly an application in nuclear medicine, and for this reason it will be Stefan.
Yeah,
is it okay?
Are you still on the first slide, or did you move on your end? Because right now we still see the first slide.
Okay, so it seems okay here. Oh, okay, sorry. Okay, sorry about that. Okay, why it's not moving here? Okay.
Oh, good.
I'm on the correct one now. So as I was saying, the TK222 resin is its main applications are in nuclear medicine at the moment, and so it will be in the presentation of Stefan at the end of this session. There will be presentation on the TK102 and 225. Under development are extractive membranes, some industrial resin, and also resins regarding the separation of cesium and rubidium that will be presented by our colleague Ilarian and some other projects. So let's move on. Okay, so as Ines presented already, we have this new resin, the TK-ATC synth. So this kind of resins are made with plastic scintillating beads that are impregnated with selective extractants. So this technology has been developed by the University of Barcelona. And the first one is the one that has been presented on the technetium. So mainly it's very similar to the TIVA. It's a quaternary ammonium plus a phase modifier that is impregnated onto beads, onto those scintillating beads. And as you've seen, this is mainly for technetium, but as the quaternary ammonium is an anion exchanger, as Ines showed, you can use it also for the chlorine or the iodine extraction and measurement. There are new resins that are in development in cooperation as well with the University of Barcelona, mainly for the measurements of strontium-19, lead-210, and for gross alpha. And of course, any other radionuclide that can be of interest will be the ones that need to be done usually by liquid scintillation, that are usually done by liquid scintillation, could be transferred onto these solid scintillators. So mainly how it works, the treatment, the first treatment. Okay. Okay, it's just that. Why? Okay. Do you see the presentation? Do you hear me? No, inform.
Yes.
Yes, it's okay. Because it says that someone took over my presentation, so that's why I'm a bit confused. So the main difference between the standard method and this scintillating bead method is just that the treatment is the same, the load and the rinsing are the same, except on the usual method, you will elute the radionuclide and then do the different measurement for the yield and of course activity measurement. For the on the beads, you measure directly the cartridge inside your scintillator counter, and for the chemical yield, you will measure the eluate after the last rinsing, let's say, and to see how much. In the case of the technetium, people usually use rhenium or maybe ruthenium So they will measure that and do the yield regarding what they have put in the first place and what they have, if there's any rhenium in the eluate phase, and this measurement usually will be done by ICP-MS. Okay, so for this one, okay. Okay, so the TK202 resin was presented by IBAC just before the break. So it's a polyethylene glycol grafted on an inert support. And what is very interesting, as was mentioned by IBAC on this resin, is that it's very suited for samples that have been fused with alkali solutions. So mainly the resin will be loaded in strong sodium hydroxide or potassium. Nope. On potassium hydroxide. Nope. Okay, if you hear me, I just have a problem. It says that I have to synchronize with the presenter, and I have no idea. So what I will do is that I will do just as Ines has done. I will, okay. I will close the presentation. Okay, that's what I was to do. Thank you. So I will try to reload my stuff here. Okay. Okay. So I will stop that. And I restart the. Okay, I'm trying to. So do you see the presentation now?
Yes.
Yes, okay. Thank you. So I will. And is this on the TK202 resin slide?
Yes.
Yes.
Okay. So as I said, so usually the load and the rinse will be done in very strong concentration of sodium hydroxide or potassium hydroxide, and then the elution is done in a very small volume of water. With of course, the eluate remains quite alkaline, and people will use after the eluate, the water eluate, will be loaded onto a cation exchange resin to neutralize the medium and to get rid of the in case of the sodium or the potassium, and then there is a load on an aluminum oxide resin to get rid of the molybdenum traces. And usually the elution of the technetium can be done in this sodium chloride medium. So that would be, so this is it. And of course, you've seen the result from IBAC in the previous presentation. So the next resin is the TK200 resin. It's not a new resin. It's quite, it's been on for maybe five years. And it's based on the topo extractant, so trioctylphosphinoxide extractant. And it's a very interesting one because it will extract uranium, thorium, and plutonium at pH 2. So it means that, and usually the pH 2 is the medium in which people are going to store their water samples or other kind of samples. And so it will help, or it will allow to do the pre-concentration and the purification of the selected actinides on the same column. So, which make it easy to automatize and measure afterwards by ICP-MS. So there are two main applications. uranium-thorium separation and also uranium-plutonium separation. So I will present you that. And there are other applications, but here again, it's for nuclear medicine, and these applications will be presented within Stefan's presentation. So here's some studies, some coefficient studies. So as you can see, at very low HNO3 concentration, you can load or you can fix americium, plutonium, thorium, and uranium. And americium will be the first one to come out. And after, depending on the acid or the concentration of the acid, you will be able to do the separation of the other actinides. Also, it's interesting because it can also be used for the tin separation. So it can be an alternative to the TBP resin. And so that's very interesting. And for the bismuth, there's also a very high uptake of the bismuth in case for lead separation. So that's that's also other possibilities. So here's some elution study for uranium-thorium separation from acidic solution. So usually the load and the rinse will be made in 3 molar HNO3, and then the thorium can be or will be eluted in a pH 1 HCl solution with oxalic acid, and the separation and the elution of the uranium can be done either in an ammonium oxalate solution at pH 9 or in a sodium hydrogen carbonate solution. And as you can see in the schemes below, there's a very neat and good separation, whatever is the medium for the uranium. So very interesting. This is the same, but here this is the same uranium-thorium separation, but here with more elements in the load solution. And what you can see is that most of them, except for the thorium and uranium, all of them are eluted during the load and the rinse phases. So thorium is very nicely and very sharply eluted, and the uranium as well. So this is one type of separation, and the other separation that can be made on the TK200 resin is the uranium-plutonium separation. So here it was made from soil or sediment, so this is no longer from acidic solutions. So the sample is pre-treated. There is calcium lanthanide fluoride coprecipitation after a reduction to remove mainly potassium, sodium, uranium, and manganese. And then the precipitate is centrifugated and dissolved into a 3 molar HNO3 solution. And some boric acid and reoxidate an oxidant for the plutonium to put the plutonium back to the 4 is added there. And then this is passed on to the TK200 resin. So the rinse is made in the same medium, and then the second rinse at 0.5 mHNO3. And finally, the plutonium is eluted in a 8.5 mHCl in presence of a reducing agent. So at this point, the uranium or the traces of uranium that remain in the sample are fixed on the TK200 resin. And what they do here is that they have done the test with one column to see the decontamination factor, and this with one column it's 1.2 times to the 5th for the decontamination factor. And if the solution, this eluting solution at 8.5 HCl with the reducing agent is passed through a second TK200 resin, in this condition, the uranium remain, or the traces of uranium remain on the TK200, but the plutonium just pass through the resin because of of the conditions. And in this case, they were able to achieve a decontamination factor that is above 7.5 times to the 7. So that was one goal of the author, was to have a very good decontamination factor and a very good separation between the plutonium and the uranium. So this is one other way of using the TK200 resin. So it's a very interesting one for solutions that are pH 1 or 2. It allows to do the pre-concentration and the separation of the plutonium, uranium, and thorium, and it can also be used for just a UPU separation, and it can be used as well for extraction and concentration of tin and cadmium. So this resin is pretty interesting, depending on what you do. The next resin is the TK221 resin. So this resin is based on a mixture of diglycolamide and phosphinoxide, plus some long chain alcohol on an inert support. The main application are for rat farm, but there's also some application for the separation of actinides. And these graphs are coming from a publication from Paps and Vajda and Apple from last year, showing the distribution coefficient of different actinides on this resin in nitric acid and HCl medium. So it's very close to the DGA performance, but with some slight difference, and this is the next step. So here for the separation of actinides, the separation of thorium, plutonium, uranium, americium, there will be again a combination of TIVA and TK221. So the TIVA is as usually used for the plutonium and thorium separation, or plutonium, neptunium, and thorium separation. And the TK221 will be used for the uranium and americium curium separation. So the load solution is a 3 molar HNO3 reloaded with some aluminum nitrate and sulfamic acid for doing the redox cycle on the plutonium. So plutonium and thorium and neptunium are staying on the TIVA resin, and americium, curium, and uranium will go through the TIVA and remain fixed on the TK221. And then, so for the TIVA, then there is a rinse with 9-MHCl for eluting the thorium. In this case, they are doing the plutonium elution in a 9-MHCl in the presence of chloride titanium, trichloride titanium. And finally, the neptunium is eluted in a 0.1 mHCl in the presence of HF. So this is for this part. On the TK221, what is very interesting is that after a wash at 4 mHCl HF, so this is to make sure that there is no traces of, or if any traces of thorium have followed, then they are gone, and same for neptunium. And finally, the americium is first eluted with 0.25 mHCl, and then the uranium. And here, usually when you use a combination of TIVA DGA, on the DGA, you first elute the uranium and then the americium. On the TK221, it's the reverse. You first elute the americium and then the uranium. And the recoveries for americium and uranium are quite good. So it's a very interesting resin as well for that. So as I said, for the TK222 resin, it's the same as the 221, but it's based on TH-DGA instead of TO-DGA. And it's about the same properties as for the TK221 resin. And as already mentioned, this will be presented by Stefan in his presentation later on. This is a new resin that has been put on the catalog this year. It's the TK102 resin. So this is a modified version of the strontium resin. There's the same chronometer, but solvent and inert support and ratios are different. So this was done by Ilarion that presented the poster during the ERA meeting. colleague Marimba and Sumaya Kalfala, and our colleague in Hungary, Nora Vaida at the Radanal lab. All was supervised by Stefan. And the method have been the current method on that are used applied on the strontium resin have been applied on the TK102, but other separating methods are under development. So here you can see the distribution coefficient values. And on this resin as well, there is very strong uptake for strontium, barium, lead, and thallium in HNO3, especially above 1 molar HNO3 or 5, depending on the element you're looking at. And in HCl medium, there is high retention for lead, thallium, tin, antimony, and gallium. On the last graph, what you see is the incidence or the how the presence of potassium, sodium, and calcium interfere with the uptake of with the distribution coefficient of strontium, and mainly up to 0.05. There is no effect of the potassium or the calcium, and there's not much effect on the sodium up to 1 m. The one that is having quite an effect is the potassium, but it's after this for concentration that are higher than 0.05. So there was also interest in doing the capacity of this resin, and what has been determined is that the capacity of the TK102 resin for strontium is around 40 milligram of strontium per gram. For the barium, it's a bit complicated because there was some limitation on the solubility, so it's not so clear what is the capacity, but on the column experiment, it was around 12-13 milligram barium. And for the lead, it's around 95 milligram lead per gram of resin. So it's very interesting. And as for the strontium, it's kind of higher than it was on the strontium resin. So here are some more data about the capacity of the resin, especially in strontium and lead, to ensure that the dynamic and static values were similar. And here, what is interesting was to compare the performance of the strontium resin to the TK102 resin for strontium and also for lead. So here what you see on top is the TK102 resin, on the bottom is the strontium resin, and the profiles are quite the same. Just the peaks are a bit sharper on the TK102 resin. And what we can see as well is that I think it's the thorium. It comes out between rinse 1 and 2. I mean, when the rinse 2 starts. Okay. For the PB, for the use of the TK102 resin for the PB elution or separation, again, the comparison between the two resins shows that they are quite similar. So in the end, this TK102 resin can be used in the lab. There's the transposition of the procedure can be done quite directly without much change regarding what we have tested here. And the last thing on this resin is the separation radium and barium. So this is something I think Stefan will talk a little bit more on his own presentation, but what is interesting when you compare the TK102 resin with the strontium resin is that the radium is not retained on those resins, but what you can look at is on the barium. There is a kind of leakage of the barium on the strontium resin that you don't see, or there is one also on the TK102, but it's very, very small and very not so high than on the strontium, meaning that there's probably a way, or one way, to do this really a good barium-radium separation. And this is something that is of great interest. So it's it's tested, and so I think Stefan has some more information about that. The next resin, the next and the last new resin, is the TK225 resin. Its main application is the removal of the radiolanthanides from acidic effluents. So this resin is again based on the TO-DGA and the ionic liquid. So the selectivity is very similar to the DGA resin, and the presence of the ionic liquid is really highly increasing the selectivity towards the trivalent element. And they are even it's becoming very difficult to remove them from the resin. So here, I hope on the screen you have, it's easy to read. You have the distribution coefficient for lanthanide on this resin in HNO3 and in HCl, and mainly after depending on the type of lanthanide, for the light lanthanides, it seems that some of them are easier to remove when you are in the low concentration, but for the heavy ones or medium ones, then they are very well fixed on the resin. In HCl, it's a bit the same. It's not as pronounced than on the in HNO3, but it's very strongly retained as well in a high concentration. What was tested also on this resin is other types of metals, and what is interesting there, it shows very good retention for calcium in nitric acid medium above 0.5 mHNO3. So at the moment, this is a very interesting property, and at the moment there are some methods under development for finding a way to do a very calcium-specific separation. And some other elements, again, were tested, and the resin is showing retention for thorium, zirconium, and hafnium in nitric acid medium, and it's showing retention for tin, antimony, zirconium, and uranium in HCl solution. So for tin and antimony, this resin would be another alternative to the TK200 and TBP resin. Okay. So this is about it for the new resin, or the not so known resin. And now I'm presenting some coming products. So there are some impregnating filtering membranes, which will allow for very fast flow rates and used with very large volumes of water, but it can also be used in passive sampling. And so these membranes are being under how to say that? They are being explored. In the presentation of Maximilian Holzmann, you saw that there was some information on the TK201 resin. So this one's mainly for the technetium, and here there's some information about it. So it was tested so it was tested there. There was 3 discs. The solution was 1 liter of tap water acidified at pH 2 and spiked with technetium. And then it was rinsed in the same medium. And what you see here is that there's no leakage on the different discs that was tested. And in the end, the technetium is recovered, and the elution is kind of quantitative, because more than 95% of the technetium is recovered. So it's it's kind of having a very good results. And for the DGT, there was already some TK100 membranes. So each time the membranes will have the same, as you saw, the same name of than the resin. So using the same extractant, but in this membrane format. And here this membrane were used for the strontium and lead determination in soils. Okay. Another topic that we have at the moment, it's the production of industrial extraction chromatographic resin. So these are coming from requests from hydrometallurgy area. And the idea is to see how to transpose the resin we have now, the ones that are of interest, into bigger particle size support and in higher amount. So the challenge here is to have a good supply of extractant and of inert support at sufficient quality, lower cost, and high quantities. And for this, there was an increase of production capacity to make sure that we can provide the bigger quantities. So this is something on. And under development, this is the cesium rubidium resins, and this is Hilarion that will present you that right after my presentation. And there was also a point on the ongoing projects, and this will be Stefan's almost last slide, I would say, at the end of this session. So I thank you very much for your attention. I hope that all of the presentation was okay with this Visio thing. And if you have any question, do not hesitate. Thank you. Okay, I don't hear you, Stefan.
Okay, now? Can you hear us now?
Yes, I hear you now. No problem.
Okay.
Tell me that you were hearing me the whole presentation.
Yeah, we did. I need to do a little sprint to get the thing unmuted before we can talk. Okay, yeah, so thank you very much for the nice presentation. Are there any questions? There was a lot of stuff. That's nothing, mine's going to be.
Do you have a chance to ask question to Stefan, because we'll talk about some of these too, so.
We can talk of that. Okay, so if there are no other questions, then again, thank you very much.
Thank you.